Hello, everyone. This webinar series has been convened by the Critical Zone Network, Early Career Network, and is in partnership with the Critical Zone Collaborative Network. This is the third week of this series that the Early Career Network has planned with the goal of enhancing collaboration and synthesis across CZ observatory and watershed sites. This is the second series that this group has put on with CUAHSI. The first one occurred just about a month ago, and the recordings for those are on the CUAHSI YouTube channel if you're interested in checking those out. This Cyberseminar series, Tools for Integrating and Synthesizing Data from CZO and Watershed Sites, is a 6-part series that will continue each week at this time until December 2nd, with a brief break in late November for Thanksgiving here in the States. My name is Julia Masterman. I'm an education and outreach specialist for CUAHSI. CUAHSI is the consortium of universities for the advancement of hydrologic science, and our mission is to advance water science by strengthening interdisciplinary collaboration, providing critical infrastructure through our data services, and promoting education in water science at all levels through programs, in part like this Cyberseminar series. CUAHSI also serves as the national coordinating hub of the Critical Zone Collaborative Network, or CZCN, and we're thankful to the members of the CZNet team for their contributions to this series. The CZNet team is hosting another webinar series kind of concurrently with this one on data management. This will consist of bi-weekly mini workshops and data help sessions by the CZ Hub team. And it's a great opportunity to ask questions and get help one-on-one from the members of the CZ Hub team. So if you're interested, I'll be posting a link in the chat in a moment, and those are occurring every Wednesday at 4 p.m. Eastern Time. But before we get started on today's webinar, a few logistical things. This webinar is being recorded and will be posted on the CUAHSI YouTube channel later on this afternoon. Secondly, we ask that you use the Q&A functionality to submit questions to our panelists rather than the chat. And finally, we expect that all involved with CUAHSI Cyberseminars promote and maintain a professional, considerate, respectful, and collaborative virtual environment. So thank you for being a part of that. Thank you again for joining us, and to the CZN Early Career Network for putting together another great lineup of presentations, and to our presenters for taking the time to join us today. This session is on data harmonization and integration, and I'm looking forward to a number of great talks today. With that, I'll pass the mic to the CZN Early Career Network Steering Committee member, Bhavna Arora.
Thank you, Julia. Welcome, everyone. I'm super excited about this week's seminar on data harmonization and integration. This is the third week, as Julia pointed out. The goal of this particular webinar series is really to learn about interoperable data, tools, models, and experiments that could help provide us directions for an upcoming AGU workshop. The AGU workshop is called Towards an International Critical Zone Network of Networks for the Next Generation Through Shared Science, Tools, Data, and Philosophy. So it's an AGU workshop that's going to happen on December 9th, totally virtually. And what we're planning to do is get together the next generation of scientists and early careers in thinking about, transdisciplinary investigations of the critical zone, but in a coordinated manner, right? So this particular webinar is providing us the tools and where those data exist to be able to do some of that synthesis and integration. So the timeline for today's webinar is that we have 3 expert speakers, and we'll hear from them, and then we'll go into a question and answer session. And with that, I want to pass this on to my cohort, Claire.
Great, thanks so much, Bhavna. Hello, welcome everyone. So today we have 3 speakers, and they are going to be discussing their unique experiences with data harmonization and integration. And I think the interesting thing about these 3 speakers is that they're going to share with you different end uses for bringing diverse data sets together. We do only have 3 speakers today. Usually we have 1 or 2 more, but I think this is great. We'll have a little bit more time for each of them to present, and I'm really looking forward to a fruitful discussion at the end that my colleague Chris Wellen will help lead. So yeah, without further ado, I'd like to introduce our first speaker, who is Dr. Cody Ross, who's a postdoctoral fellow at my home institution, which you'll notice says ex-university. Our university is undergoing a name change right now, so we don't use the old name of the university. So Cody, if you'd like to go ahead and share your screen.
Yeah, okay, is that visible there?
Yeah, that's great, thank you.
Okay, perfect. So thank you all for attending. Today I'm going to speak about process-based techniques for data integration that help to bridge the gap among different uniquely characterized watersheds. Specifically, I'm talking about the theoretical and logistical utility of using hydrological thresholds for complex system characterization. So hydrology has relatively few governing laws and theoretical principles that are broadly applicable. So knowledge generation in the discipline is largely from individual studies that intensely characterize processes for one or a limited number of experimental hill slopes or small catchments. And these types of investigations, they've really been instrumental for understanding catchment function. And really most knowledge about runoff generation has come from process descriptions of nearly pristine research hill slopes and catchments in humid environments. So these studies have also provided the necessary insights and data for the development of hydrological models. There are also some consequences to these isolated studies, specifically low transferability of some findings. So the low transferability of some findings in hydrology is in part due to the lack of tools for connecting and comparing process descriptions of unique places. And I think that synthesizing data from a broad range of environment towards the development of such tools is likely one of the most effective ways to advance broadly applicable theoretical concepts in hydrology. So one potential framework for cross-site synthesis and data integration could be developed around hydrologic thresholds. So in recent years, the low transferability of findings has motivated a shift in focus towards emergent properties that may serve as valuable tools for describing and characterizing hydrologic response. So emergent properties, they cannot be predicted from individual landscape components, and thresholds and rainfall runoff responses are an emergent property that reflects process and landscape heterogeneity. So thresholds of this type, they're broadly defined as a critical moment in time or point in space at which runoff behavior rapidly changes. And they've been described as catchment functional traits and signatures of watershed behavior. So there are currently an existing set of diagnostic shapes that have been proposed that integrate process and landscape complexity into a simplified form. And these include the classic hockey stick or dog leg threshold shape, the step or heaviside function, the Dirac function, and the sigmoid functions. So these thresholds, they're not merely important considerations for theoretical or comparative purposes. There are numerous studies that have shown highly variable and threshold mediated responses, and they're sensitive to specific precipitation volumes, rainfall intensities, soil moisture storage, and water table elevations. And because of this, thresholds are now really essential for conceptualizing runoff generation. So thresholds, they're generally associated with increased runoff as well. And a better understanding of threshold behavior, it provides insights on flood forecasting and water quality. So to really demonstrate how hydrologic thresholds can be used for data integration and synthesis across sites, I'm going to briefly present work on the ubiquity of threshold behavior and rainfall runoff event responses over a wide range of environments, in addition to the integration of threshold behavior into modeling frameworks through the evaluation of process-based model fidelity. So this work, it focused on one hill slope and 20 catchments of 7 study areas that spanned 4 different countries. These study sites and areas differ in terms of drainage area, climate regime, topography, land use, and subsurface properties. So first of the sites in Canada is the Catfish Creek watershed in southeastern Manitoba, the Lake 658 UP1 catchment of the ISD Experimental Lakes area in northwestern Ontario, and then the Hermine catchment in Quebec. In the United States, we have the Panola Mountain Research Watershed Experimental Hill Slope that's in Georgia, and then 8 nested catchments of the H.J. Andrews Experimental Forest in Oregon. And then in Australia, we have the Tarawara catchment near Melbourne, and finally 8 sub-catchments of the Mahurangi River catchment near Auckland, New Zealand. So the site data that were used in this analysis included records of discharge, rainfall, temperature, some topographic data, as well as soil moisture data. And across study sites, the data record duration, it ranged from 6 months to 5 years. And the observation frequency differed and was arranged from 1 minute frequency to 1 hour frequency. These data, they're aggregated to a 1 hour frequency for consistency among the sites. And then they were used as input data for a MATLAB toolbox called Hydron. And that's used to delineate rainfall runoff events. So that tool was used to delineate over 1,600 rainfall runoff events. And these events were then subsequently characterized individually using meteorological factors and response metrics that form the input and output relationships that we evaluate for thresholds. So for meteorological factors, there are 15 measures of rainfall depth, and they're related to storage-driven processes, 2 measures of rainfall intensity, and then 14 measures that quantify hydrologic extractions that are caused by evapotranspiration. So they're related to intensity or combined storage intensity-driven processes. So some of these factors, these meteorological factors of rainfall depth and evapotranspiration, they were quantified over different antecedent durations. So they were assessed for 1 to 30-day durations. And then for response metrics, there were 10 different variables that were used to quantify different aspects of event hydrologic response. And these response metrics, they provide first order information on how a specific catchment is functioning. And 6 of these metrics, they're related to the timing of the hydrograph. So for example, the hydrograph rise and peak and things like that. And then the 4 other metrics, they're related to response magnitude. So again, the meteorological factors, they're the input part of these relationships, and then the response metrics are the outputs. So these meteorological factors and response metrics for the 21 sites were used to construct over 5,000 different input-output scatterplot relationships. And using piecewise linear regression analysis and a robust statistical criteria, I evaluated these plots for threshold behavior. So this allowed for 3 questions to be addressed that were aimed at assessing the ubiquity of thresholds in rainfall runoff event responses. So first, the ubiquity of total event rainfall thresholds for response magnitude were evaluated. And those were isolated since they're the ones that are most commonly reported in the literature. Second, the remaining factors and metrics were used to determine if different variables were also associated with different threshold behaviors. And then finally, meteorological factors quantifying antecedent conditions. They were used to see if threshold behavior is dependent on antecedent conditions over short, medium, or longer term durations. So in the figure on the right, the y-axis shows the different sites that were assessed, the 21 sites, and the x-axis shows the different types of meteorological factors that were considered in these threshold relationships. So if a black square is present, that indicates that a threshold was observed involving that type of meteorological factor. So in this plot, the presence of thresholds for response magnitude only is shown. So we're not talking about response timing. So many sites had rainfall depth thresholds for response magnitude, and most common were rainfall depth thresholds that accounted for both total event rainfall, but also antecedent rainfall. Rainfall intensity, potential evapotranspiration, and effective rainfall were also important controls on threshold behavior, but only for some sites. This analysis also showed that thresholds are sensitive to different antecedent conditions over specific durations, and that those vary depending on the site and factors that are considered. So the take home of this slide is that hydrologic thresholds, they're observed at 20 out of the 21 sites. And this confirms the near ubiquity of threshold behavior in rainfall runoff responses for these different environments. So like I said, a wide variety of threshold behaviors were detected, and this really allowed for the development of a typology of threshold dynamics. So this is the map or qualitative tool that can be used to integrate rainfall runoff response information from multiple sites in a process-based way. So this typology, it distinguishes 7 different types of threshold dynamics, and they're based on 3 different criteria. So the first criteria is based on the number of response metrics that simultaneously change behavior at a single critical meteorological factor value. That's kind of a mouthful, but this indicates whether thresholds are restricted or if they're pervasive. It's an indication if multiple aspects of hydrologic response are affected by specific input values. Secondly, whether thresholds are observed over short or long antecedent durations, or both, distinguishes threshold dynamics on their sensitivity to antecedent conditions over time. So thresholds can be characterized as short memory, long memory, or memory independent. And then finally, threshold dynamics can be categorized based on the processes that they depend on. For example, a threshold dependent on only rainfall depth is indicative of single process threshold dynamics, namely storage, while a threshold influenced by both rainfall depth and rainfall intensity is associated with multi-process threshold dynamics. So this type of topology is intended to be rather flexible. So if you were to say bring in different types of meteorological factors or say soil moisture data, it would be adaptable to those different types of metrics that are being used. So these hydrologic thresholds, they're pervasive, one, and two, they can be used to functionally characterize real-world runoff responses. They can also be used to characterize the hill slopes or catchments themselves. So I'm also going to talk about how these thresholds can be used outside of site comparison for constraining rainfall runoff models. So in this case study, a subcatchment of the Maharangi catchment in New Zealand was used to evaluate benefits of constraining outputs from a rainfall runoff model using these thresholds. So 500,000 Monte Carlo simulations were ran using a simple rainfall runoff model. And they're performed using parameter values that were randomly sampled from the feasible parameter space. So I used the KG score of each simulation to kind of separate simulations into a behavioral category and a non-behavioral category. So this process is rather arbitrary, but a cutoff of 0.3 was used, and only about 8,000 of these 500,000 simulations actually were deemed behavioral. So I guess the bulk of the work is actually in assessing the behavioral simulations on their ability to reproduce threshold behaviors. So similar to the observed data, these simulations were separated into events, and then the factors, the meteorological factors and response metrics were calculated. And then I evaluated how well the threshold behavior at this site was replicated by each of the simulations. So for this particular site, 5 of the input-output relationships that I discussed previously had threshold behaviors. And among these 5 thresholds, between 48 and 97% of the behavioral simulations reproduced the threshold with a low amount of bias. So when I say low bias, I mean not only referring to the inflection point, but I'm also talking about other factors like the pre-threshold and post-threshold slope. So many of the simulations, they adequately reproduced one threshold or a combination of thresholds, but fewer simulations adequately reproduced all 5 thresholds. And this suggests that using a range of different thresholds in model evaluation might effectively distinguish among simulations that can reproduce different aspects of response related to each threshold. I'm not going to dive into it too much here, but there's also the ability to use these thresholds to actually constrain the parameter space based on catchment function. So I mentioned, I'm going to give you a little bit of a summary here because I'm kind of running into time, but I mentioned at the start of this presentation that hydrology is largely non-theoretical. And historically, there's been a focus on characterizing processes for relatively smaller number of environments with a focus on articulating heterogeneities. So comparative studies, they facilitated by sharing between different research networks, it rather allows for a shift in focus from heterogeneity to characterizing common threads that exist across the diverse environments. So emergent threshold behaviors are one of these threads, and in thresholds and runoff response are nearly ubiquitous, so they're functional in this way. Additionally, their applicability is both applied and theoretical. So you can use them to characterize and better understand hydrologic response for individual catchments, or you can use them in a more broader way to characterize catchments overall. So the topology that I offer today shows one way that complex threshold behaviors can be distilled down into a classification scheme that is facilitated by data integration and allows for watersheds to be classified based on runoff controls. These thresholds can also be used more directly as a physical realism constraint in modeling exercises like the one I showed, which further increases the usefulness of this data integration tool. There are also more opportunities that lie ahead of this work to increase the utility of threshold behavior. So evaluating thresholds over longer periods is still very uncommon, and characterizing long-term temporal variability in thresholds may be an indication of resilience as watersheds experience different anthropogenic stressors. And then lastly, on the modeling front, I think that thresholds prove to be useful in model evaluation in a post-calibration context. And this proof of concept opens up the door for automated routines that identify parameter sets based on their ability to reproduce a range of threshold behaviors that are observed in reality. So that's all. With that said, I'd just like to acknowledge that this work was part of my PhD, that was co-supervised at the University of Manitoba by Dr. Genevieve and Dr. Christopher Spence. And I'd also like to thank all the people that helped me obtain all the data that was used in this synthesis, as a lot of it was not publicly available.
Great, thanks so much, Cody. That was wonderful. That's a really great example of how data integration can lead to a very deep cross-site synthesis. And yeah, I look forward to discussing it more. So we'll move on now to our next speaker, who's Dr. Kathe Todd-Brown, an assistant professor in the Engineering School of Sustainable Infrastructure and Environment at the University of Florida. Great.
All right, let's see if I can get this. Okay. Well, thank you for the opportunity to come talk. We're going to move from the hydrology sphere to the soils. And so what I'm going to be talking about today are what I like to call wordy soils, so semantic tools for soil data harmonization. Sort of using soils here as a demonstration system, but a lot of what I'm going to go over for soils is more broadly applicable to the critical zone in general. All right, so it shouldn't surprise anyone here that because soils and critical zone are really rich and diverse systems, we need a rich language in order to describe that soil data. And I just did a sort of a brief brainstorm on some of the terms that are commonly associated with soil data sets. And this includes things like geolocation, time, local vegetation, site history, local climate, parent material, color, horizon, bulk density, elemental analysis, texture, and the list goes on and on. And so you can imagine that if you're looking to find data of a particular type, you need to be able to teach your search engines what each of these terms mean and how they're interrelated. Oh, there we go. All right. So harmonization tools and semantic tools in general were primarily developed for discovery. So this is sort of similar to creating a Google search engine for data repositories. So say you want to look at bulk density data in soil, you just have to teach your search engines that bulk density is a term that can be related to soil in this very specific manner. On the flip side, if you, or in contrast, if you're interested in data harmonization, you need a different tool set that maybe has a finer resolution on what those terminologies means. So if we take the example of bulk density, we can talk about fine earth bulk density, and then we can get even more specific, saying that maybe we want a 2 mil sieve size of a 2 mil dry sieve bulk density. So the semantic tools that you need for this very specific data harmonization are slightly different than the semantic tools that you need for data discovery. And so this sort of comes up against what how a lot of these projects work, which I like to call the student method. This is also manual data transcription, where you essentially lock a student in a small room, generally, with one or more data sets and say, don't leave until you've got one data set to rule them all. So there's lots of manual transcription. The advantage of this is it's relatively easy to teach once you, especially if you have a student with some domain knowledge, so they know what types of data can go together. The disadvantage, it can be difficult to revise the template. So if you've started on some of these longer projects, maybe started with one target data template or data format that they wanted to get to, but along the way discovered, oh, I need to expand the data template. I need to discriminate between these terms maybe a little bit more closely. So with a manual transcription like that, it can be very difficult to go back and do these revisions. You often end up leaving information behind. So these data templates can be maybe for an individual study, they measured something else, and that else thing was not included in your data template. Depending on the use case, this might not be a problem for you if you're only developing it for a single purpose. But if you're looking to reuse the same database, then sometimes that orphaned information can become a problem. And then finally, it's difficult to maintain what data provenance and reusability, so that general use case that we talked about previously, but also tracking where each data point came from. With a manual transcription method, at some point you're saying, this is our source data, trust me, this resulting data that you're looking at now ties back to that source data, and maybe you converted the units and you dropped a 0 when you did your unit conversion. Done that. So by doing this manual transcription, you can sometimes introduce these errors, and because you don't have that traceability of sort of a code record for how the data was munged together, there's a trust me aspect to it that maybe is not entirely necessary. All right. This is by far the most common method that we ran into when we did a survey of some of the larger soil data aggregation groups. Of the 8 groups that we talked with, 7 of them used a manual data transcription. So they developed this big spreadsheet, and then they farmed it out to mostly graduate students to populate and then knit it all together. So if you go through this exercise as a student, at some point you're going to say, aha, if we only had a master data template to rule them all, some idealized data standard that all soils could talk to, then that would solve all of our problems. The problem with this master data template approach is that it is both at the same time too big and too small. So many of these larger integrative studies will end up with 100, 200 columns in their data template, and it's very laborious to go through as a data user to populate and understand what each of those data columns mean. At the same time, most people also find that it's too small. So maybe there is a novel measurement that you introduced in your study that's not in that data template. What do you do? Or maybe there's it's difficult to describe maybe an experimental treatment or a field manipulation that was done at that site, and difficult to introduce into these data templates. So as a result, this slide here sort of traces the development of one soil data template that was initially developed by the USDA NRCS for soil survey data. Was influences WOSIS, which modified it to be more globally applicable. ISCN, which is an organization I'm the data manager for, picked that up and combined it with one of the early Ameriflux's templates. It then got passed to ISRIC and SODA, who modified it slightly for radiocarbon and fractionation information, and then SODA had to tweak it to deal with long-term repeated observations. From the radiocarbon group, you also saw an incubation data set pulled together, which took an even different approach, where they represented it as this interesting nested tree instead of a template format, which was very efficient from a memory standpoint. And then the Coastal Carbon Network further modified the ISRAD data template to work specifically with some of the coastal information, focusing a lot on accretion and age in soils. So this is an example of just one data template that's sort of morphed over the past decade or so into things that were quite different from how it was originally envisioned. So master template seems like a good idea, and then you start looking at the nitty-gritty and it starts becoming a little bit more complicated. But there are other semantic tools other than just using a template that could be a community resource that we could draw on to aid these data harmonizations. All right, so in contrast to that data template approach, there is a generalized data annotation approach that you can take for harmonization. And this was really kind of exemplified by the SODA project led by Will Weider et al. That looked at integrating LTAR and NEON data sets and a few other long-term observation data sets. And they sort of followed on this idea that was sort of proposed by the Environmental Data Initiative of level 0, level 1, and level 2 data. So level 0 data is your raw data. So that is the stuff that you would put on repositories or that you would host as public facing in its own individual format. If you can combine that with the right metadata annotation and link the vocabularies and the data structure of the original raw data to a target format, you can then generate level 1 data. So everything is now in this harmonized data format, specific, generally a CSV file. And then now, once everything is in the same data table, then you can start doing those row binds and push them all together as a single data product on level 2. One of the really nice things about this type of annotation-driven approach is that you've got a very explicit linkage between the 3 levels. So you can maintain that traceability and that data provenance, and you know exactly what was done to each data point in your final database. Right, okay, so if we're talking about informatics and soils, you have to mention ISRIC, which is the World Soil Information Service, associated with the UNFAO. And what they are responsible for are hosting big regional databases. So they primarily focus on soil surveys as opposed to experimental data. Yes, so they use sort of this blended approach where they write an individual script for a particular data set that maps to their internal data standards. So they've got a lot of interesting documentation and reports. What they don't have is necessarily a vocabulary service. And I'm going to talk about what I mean by a vocabulary service a little bit later on. But if you're interested in soil informatics, ISRIC is definitely a place to be aware of. Right, so the promise of big data. So what you want to be able to do is to say what you want and get it. So something like, give me bulk density data from anywhere that is measured without pedotransfer functions, fine earth of any sieve size in a single data table. So we have specified here the location and the time that we are interested in. The measurement, so the observation type, so bulk density, organic fraction, pH, something along those lines, and then methodology. And so that third methodology is probably the most complicated to try to capture because that requires extensive domain knowledge. So an informatician is not necessarily going to know that a sieve can be a dry sieve or a wet sieve, and that those are sometimes different for different purposes. But that is something that a domain expert would be aware of. So developing that methodology to then go back and annotate your data with, that method description and vocabulary list that you can then go back and annotate your data with is particularly important. All right. So talking about related terms and measurements. So if we think about observation types, those observations can be related to each other. So for example, bulk density is related to coarse fraction. So coarse fraction is the big stuff that you sieve out, and you generally report it as, say, a volume fraction. And you use that to calculate soil carbon stock. So a lot of the current ontologies are focused instead on those measurement types. So bulk density versus the fine earth sieve example. And they typically rely very heavily on Wikipedia, which I found quite amusing when I started becoming more involved with this group. And they generally lack that specificity that we need for the measurement annotations for for harmonizing data sets themselves. But one interesting part about this is that that Obo Foundry in particular is community governed. So you can go on and propose changes, review proposed changes, and vet updates to this documentation. And that can be really important if you're thinking about extending the methodology to new omics measurements, for example. Maybe 20 years ago, we weren't measuring proteomics, but now that we've got an increasing data set that's focused on the proteomics of soil pore water. So how you go about modifying and updating these types of lists is something to think about. All right, next step. So I'm going to focus on this community-driven part and thinking about how you can curate and revise these vocabularies, which are sort of the term definition pairs or the ontologies, relationships between terms. Thinking about how you can go creating these reusable annotations so that different groups can put together different data products from the same level 0 data sets. Access and ingestion scripts. So once you have discovered the data set, APIs to automate data ingestion in R or your language of choice. And all three of these are opportunity spaces for research community development and governance. And with that, I'd like to say if you're interested in finding out more about ontologies and informatics, that the Earth Science Information Partnership is an excellent place to go to. A really interesting blend of informaticians, remote sensing, and boots on ground field scientists. I'd also like to thank the National Academy of Science and Engineering for the Exploring Dynamic Earth Information System workshop that was put on over the summer. And finally, the large number of students in my lab who've helped me think through how to go about doing this. And with that, I would be delighted to continue the conversation offline or in the Q&A section here. You can reach me at Todd-Brown@ufl.edu or find me on Twitter.
Fantastic. Thank you so much, Kathe. That was so interesting. I think there'll be lots of questions at the end. Okay, so we are going to move on now to our final speaker. Dr. Sylvie Gall joins us from the Universite Genoble Alpes, the Institut des Geosciences, it's hard for me to say, de l'environnement. Try my best to say it in French.
Okay, thank you. So, attends. So, I am Sylvie Gall. Thank you for the opportunity to present our work. I'm a French hydrologist working on critical zone observatory in West Africa. But here I will speak you to the French information system for critical zone observatories called DEA-OSCAR and make a focus on data harmonization and integration in this work. Of course, I'm not working alone. There is a team. You can see all the name here on the slide. So which observation are we talking here? So OSCAR is a network of 21 critical zone observatory made of critical zone observatory already existing before the creation of the network. They all were studying the critical zone, and the object of interest are watersheds or rivers, aquifers, glaciers, permafrost. And we make a study and find that there is more than 300 different variables observed. They are physical or chemical variables. They are regarding water, sediment, and solute balance. Also the surface energy balance. There are geophysical exploration and land use. You can see here the map of the different instrumented sites. They are mainly based in France, but you can see that there is also some other sites all over the world, mainly in the southern countries. The measurement we treat here are mainly time series for weather, hydrology, or chemistry time series, but there are also other types of measurements that by now we have not taken into account because we have chosen to begin with time series. So to summarize OSCAR in a nutshell and in 2 words, I would say it's heterogeneity and a committed community. It's heterogeneous because there is different observatories with different histories, different objectives, and by the end, different database. And the community is very implied because the researchers are sometimes working for more than 20 years on their observatory, and they know it very well, and they have a lot of ideas about what's going on these watersheds. And there is also IT engineers, and generally they are happy to exchange with other IT teams because they are often isolated in their observatory. So what is TEIA OSCAR information system objectives? So it's built in common with OSCAR. I just presented to you. It's a network of 21 CZOs. And TEIA, which is a French data center for continental surfaces. And the objective is to facilitate the discovery, the access, and the real usability of data on a single portal, so that the user don't have to know everything about the different observatory to get the data they want. And we also want to enable interoperability with other computers and other databases. So we have to comply international standards. And in general, we try to have a fair approach. So what did we do for data harmonization and integration? Here is the data flux we choose to construct. We did all the choice with the community of the different data producer. So you have different CZOs having different measurements. They all have their own database. Some of them don't have a database, but only a collection of files. To put the data into the information system, they have to write an information extraction application. And so they can be read by the pivot data model. And then the data are integrated into the database, and so that we can have interrogation for scientific user who wants to know what kind of data is available on their area of interest, or every question they can have. The information system also has to answer the question of the data producer, for instance, who has used my data, how many times, and follow the publication made with the data sets. And the data can also be harvested by computers. So the pivot data model, we have chosen to have a homemade pivot data model because we have a lot of different purposes, and there is not only one standard model that complies every needs we had. So we want to have a possibility to discover the data about variable names, geology, climate, funders, area of work, etc. We implement standardized metadata and data exchange web services. And we also have detailed information on landing pages so that we can have or produce data DOI. So to summarize, there is a very rich data description for observation and data sets. For this, we are based on different standards. Here is a list. I think it's not the main objective to know everything, but we made a mapping between the different schemes to see which metadata are common or not, and try to give the information for all the different standards. So here is a description, more precise description of the metadata. So you see information related to the description of the observatory itself with the producer identification, the funding, and etc. Some of the metadata are mandatory, others are optional. so that it's not too difficult to give all the information the first time you have to put your data in this information system. There's also information on data sets and observation description. We use observation and measurement standard. It's interesting because it describes not only the results, the measurements, but also the procedure of acquisition, the variable names, and a thing we think is very interesting. Interesting. It's a feature of interest. So here is an example of what we did about the thesaurus, but because at the beginning we asked everybody which variable are you using, and if we just list all the variables of the different observatory, we found 3,000 variables, and hopefully it was only 300. So for that, to do this job, we choose controlled hierarchized vocabulary based mainly on existing vocabulary, like NASA GCMD for the physical variables and Cendre for the chemical variables. So now all the variables are described here on the web with a semantic web standard called CUAHSI. You can see here on the bottom right a page of CUAHSI for one variable. And what is interesting is that we can easily make, we take time to put all the link with other theory, environmental theory, Antes, Agrovog, Earth thesaurus, etc. So it can reach different interests. Finally, here we can have an harmonized presentation of the measurement, Institut measurement of this network. So we can ask and find the data by different way, by the name of variable, the category of variable, also by feature of interest, temporal extent, producer, funders, etc. There is a lot of criteria. By now, it's only the beta version. We want to improve it. And the further steps are the following. We want first to increase the number of data available in Theia Oscar portal, because by now there is 10 observatories and we have an objective of 21. And all the data, all the observatory were not able to write the script because they have not all IT team or time to do it. So now our objective is to help them to write these scripts. The second future step is to expand the data discovery through thematic object of interest, for instance, river, watershed, but also country, department of different geographical feature of interest. We want, by now, we can only have data discovery, so we know that the data set does exist, but we cannot download it on our portal. We have to do that. The user has to go to the data producer portal. So in the next year, we want to implement data extraction services. For that, we have to define a format. So just before Kate shows that she also needs harmonized data files. And the last point we want to do is to implement a standardized data exchange web service, so that all the data we have, if they are correctly standardized, can be read by other computers and other database worldwide. By now, it's mainly in France and Europe, but it's exactly the same for larger community. So if you want to have more information about our project, there is here an article. There are also different websites where all the data are available, because our idea is to make free development so that a large community can use it if interested. So thank you for your attention.
Thank you so much, Sylvie. That's a lot of work to pull together all that data. So I'm going to pass it over to my colleague, Dr. Chris Wellen, who's going to lead discussion. We have about 10 minutes for discussion.
All right. So first, I want to say thank you so much to our speakers. I really enjoyed all three of your talks. We had a really nice talk from Cody about looking for thresholds as emergent properties of catchments. A really interesting talk from Kathe about integrating soils data using semantics, and another interesting talk from Sylvie about integrating critical zone information across an existing network. So the questions that I'm going to pose are ones that I think you could all weigh in on and give some insightful answers to. The first one is, how do you have any general advice about what is the best way to gather, store, and manage data? You imagine you're telling a critical zone, or someone who manages a critical zone observatory or is thinking of collecting data that would want to be able to someday integrate into some kind of a larger synthesis. What are your advice in terms of how do you gather, store, and manage the data to enable that?
Sylvia, you might be the one with the most experience in this.
It's a difficult question. We speak a lot with other community, for instance, oceanographers and etc. And we find that generally it's very important that the database is close to the producer. Because even if when you centralize all the information, it has a better technical level, but it has the risk to be far from the interest of the data producer. So in our case, we choose to keep the existing databases where people are very active criticizing the data, and they have also to sauvegarder to keep the data, not to lose them. It's not our work to do that. We only give the possibility to the discover and after that to download the data. But by the way, in fact, we have a copy of all the existing data to be quicker to furnish them. So in fact, we have them, and as far as we have them, even if it's not a long-term memory, we keep it and we save it, and so it does exist, and it's double use. And I think on the long term, maybe it's not the best solution to do, but the idea is that now we are, after 2 years of work, we are going to make a turn in France, a video turn, and see each observatory and ask them, are you happy? What do you think we have to change, etc. And we will see if on the long term we will keep this method. Maybe it's not the best, but we begin like that.
Okay, thank you. So I see our other two panelists' hands are up. Cody, I did see your hand go up earlier. Maybe you can weigh in on this.
Sure. Yeah, just to kind of mirror some of the things that Sylvie was saying, I think that it's really important on any project to start as early as possible with actually creating a repository for the data. You only kind of acknowledge the flaws of the data as you work with it. So if you're doing it all post hoc, I think that that's a really big problem if you're going to be synthesizing that data with other sites after. That, and one of the problems that I really experienced when working with multiple sites, especially in a modeling context, is that I think that it requires a lot more effort at the start of a project to characterize the uncertainties of input or data sources. So specifically the type of equipment that's being used, and characterize the uncertainty that's related to measurements. is something that's absent from a lot of the synthesized data sets that include information from many watersheds.
So I guess I'll cover the basic informatics. ASCII files as opposed to proprietary file format storage so that the data is recoverable long-term. A permanent DOI or repository to host things at. So even if it is updated later, you have that sort of long-term hosting from someplace like the Environmental Data Initiative or ESS Dive, a repository that's kind of committed to long-term permanent hosting of data sets. And then versioning of the data sets. So like Cody was saying, inevitably there's a problem with the data, or there was an annotation that someone wants that wasn't registered with the initial data set. So if you have versioning on your data releases, you can tie some of the analysis and the post hoc analysis to a particular version of your data set to improve transparency. And then finally, just being willing to talk with people who are reanalyzing your data sets. I can't tell you how valuable it is to be able to send an email or pick up the phone and talk to someone who collected the data. So that in and of itself is really valuable.
Thank you. I see Bhavna has her hand up.
Chris, I just wanted to follow up. This was such an exciting discussion. So, Cody, you mentioned, about uncertainty and even uncertainty beyond just like measurement errors and instrumentation. So, Kathe, of course, provided us an overview of what that means in terms of version control. I wanted to get the feedback from the panelists about how important it is to communicate that uncertainty, because from a modeling perspective, I feel like sometimes we miss out on what the uncertainty is within the data and how that translates into what we're getting out of the model. So what are your thoughts on how that should be communicated within these databases?
Yeah, so I think that like including that type of uncertainty analysis about the input data is absolutely critical. Almost all of the kind of end users of information derived from modeling studies, publications, all of these places that we're kind of doing this work to kind of be presented in are demanding information about the uncertainty associated with predictions. And it can't really be done completely without a good grasp on the input data. So if that information is absent at the start, then there's no way that you're going to be able to constrain any type of quantitative figure about uncertainty with the predictions that you make with that data. So I would say it's absolutely critical.
So my mother was a chemistry teacher for a very long time. And so she drilled into her students significant figures, like you don't record more significant figures than you can actually support with your instrumentation. Something that I've noticed in my own students is that after you read in a data file, the computer will extend that significant figure for you, and you'll start introducing sort of numerical error, so it will look like a much more precise number than it was actually recorded as. So I think one of the things that I would like to see moving forward in the field is reporting either precision or some kind of confidence interval in association with a particular measurement that was maybe independent of the number that was recorded. Something like, I don't know, if you took litmus paper with pH, no one takes pH litmus paper, but if you did, the uncertainty for that is maybe 0.5. As opposed to a bench measurement that you're sticking in a probe where it's maybe 0.01 or something like that, and have that be associated with the meta information as opposed to captured in this reported precision of how many significant figures do you have on your data set.
Thank you. Yeah, that was valuable.
Yeah, thank you so much. Do we have time for another question, or do we need to break now? It is just about 1.
I think we should break.
Okay.
Yeah.
Unfortunate. We could talk all day about this.
There's never enough time for discussion.
I know. Well, thank you so much again to our speakers. That's all, I guess, is all we have to say to break now. All right.
Yeah, thank you all. I mean, for everybody for joining, and thank you, Claire and Chris, for organizing, and what a wonderful set of panelists that we had today. Please join us next week. We are going to be talking about statistical and information processing approaches. So thank you. Have a good day. Bye.
Thanks, everyone.
Bye-bye.